Welcome to After Hours Engineering, Episode 12. We're now on the final set of instructions, the U type, which is just two instructions, and the JAL instruction. It's the JAL that's the remaining of the swizzling, and it's the ones we're going to start off first. So let's not waste time, let's go. As usual, we're looking at the JAL, so we'll start at the data flow diagram. Again, we assume that the instruction register has been loaded with the JAL instruction, and which means that the immediate value is present and the destination register is present, because the destination is going to hold the return address. So again, what do we have to do in order to pull off this instruction? Well, it's a two-step part. The first step is calculating the target address, which means we need to take PC prior because that has the address of the instruction itself, whereas the PC is sitting one ahead. So we'll take the PC prior. We'll also take the immediate value that's in the instruction. We'll compute that and route it all the way back immediately into the program counter so that on the falling edge of the clock we can load the program counter. Once we make it to that next phase and the PC's been loaded, we're ready to do the second phase, which is the return address, and that again is stored in the destination. So for that, we need the PC prior. That's the address of the instruction that's executing right now, which is the JAL, and we need to add 4 to it to get the next address in case we want to return. So we take PC prior and we take 4, we add them together, but this time we route it this way down the immediate path and into the destination, and on the falling edge the destination register is loaded. Excellent. Now let's take a look at the FSM, and as usual the first thing we'll do is add an entry into our decode statement that will add a new pathway and route us down a new execution. That new execution is the JAL. So as usual, we start at the first state, and this one is going to calculate this target, which means we need that prior PC value. We need the immediate that's embedded in the instruction, and we're going to route it immediately back to the PC so that we can load it when we transition out of this state and into the next state. But we're also going to check to see whether the destination is X0. If it is, we're just simply going to go straight to the prefetch state, which is going to do that memory read up here. Otherwise, the second phase is going to calculate the return address because it's obviously not X0, which means we still want the prior, but we want to add 4 to it to get the return address, which is the instruction after the JAL. And we're going to route it into the destination register and write, and then we go back to the prefetch stage because we're not setting memory read ourselves, so we'll go to the prefetch and set it here. And there you go. Here we are at the HDL, and as usual we start at the decode statement and add in our new pathway into the execute state. And that's what we've done here. So if we scroll down to the JAL, we can see that the first state, remember, is going to set up the jump address, which is relative to the actual address of the instruction itself. So we need the prior and we need the immediate. The PC itself again has been moved forward in memory. We also will need to grab the immediate results from that and set up to load into the PC register. Then we check to see if we are short-circuiting, in this case, the X0. If we're trying to set up a return address into X0, there's no point to that. So we just simply go back to the prefetch stage. However, if we are into, say, X1, then we do need to do the write back for the return address, and that return address is calculated right here, as you guessed. It's again the current address of the JAL instruction plus 4, because we want to return potentially back to the next address after the instruction itself. And again, we grab the immediate, but we route it into the WD pathway in order to set up our write back. We're now ready for the machine code. So let's get started. We're going to do 3 different versions of the JAL. We're going to jump forward, jump backwards, and jump and return. So let's take a look at the jump forwards first. Here's our instruction, the JAL, and we're going to purposefully use the X0 because we don't care about the return address. and we're going to jump somewhere. In this case, we're going to jump down to address 5, load the X2 with whatever X4 is pointing out, which is C, and I happen to know that that is A0A, and then we stop. So if everything worked correctly, we should see X0, X2 loaded with A0A. Here we are in the simulation just after the reset for the JAL instruction, the jump and link. We can see that it has identified it as a J-type, correct? And here is our machine code for this. It's also in the decode state. Remember, we set the next state for the execute, and sure enough, it is moved over to the JAL state. And remember, in this state, we're going to calculate the target address to jump to, which is PC prior, and PC prior is set to 14, coming right there, and we're going to add 4 to it, which will give us our destination address, and it comes out as PC source. We know that that is going to be used to read from memory the instruction, and there it is. It's found the next instruction to read, which is at this address, and there's the instruction. We also know that in the decode state right here, we're going to increment the PC by 4, which also gives us 18, which is kind of meaningless at that point, but that's okay. We always increment in the decode state. However, because this is the load, we're going to go through all of its states and load the register with the appropriate value, and there's that A0A being loaded into its register. So this jump and link instruction has done exactly what it needed to do, and we know that at 18 is the E-break, which is the black hole for us. So excellent, we know that this is working. And of course, the very last thing to check is to make sure, because we were loading the X0 register, we skipped the JAL RT state and went straight to the prefetch, and that's exactly what we're seeing. Now we take a look at jumping backwards in memory. It looks almost identical, except this time the JAL is lower in memory and we're jumping backwards, and we can definitely tell that by seeing that the immediate value is a negative number. The leftmost bit is certainly signed. This is actually the 2's complement of where we need to jump to, which is the address 4. So this is the instruction. So the way it'll work is we've had to set our reset vector to point to 14. It'll execute this, which it'll jump immediately up here, do a load of X2 with this value here, this address, effective address, and then we'll break. Now I know that 10 added to 28, which is the contents of 4, will actually load Bob in it. So we should see in the simulation that this time Bob has been loaded into X2. Here's the simulation for the backwards jump. And again, it's detected as a J-type, and you can see our machine code for that backwards jump. There's the negative part, the 2's complement of the relative jump. And again, we can see we're moving, because we're loading the X0 register, we don't care about the return address. It's going to automatically go to the prefetch stage. And there is the same PC prior plus 4. Everything is the same. It's going to calculate, only this time it's going to go to a different address, which is 8, to find where it needs to go. And sure enough, at address 8 is our load word instruction. We're also executing the rest of these states right here, which effectively loads the destination register right here. And sure enough, we see Bob. So the backwards jump is also working as well. Excellent. Here we are at the simulation for the jump and return variant of the JAL. You can see it sees we're starting off at the J type. There's our machine code. As before, we take our prior, PC prior, and we add the immediate that's embedded in the instruction itself, and out pops the target address that we'll move to. Also, because the destination or return address register is not 0, we do have this extra state, the RTR. If we drop down here, you can see that we're adding in 4 plus 4, and that gives us our return address. Remember, the return address is calculated by looking at the address of the instruction itself, incrementing it by 4, and that gives us our return address, and here we are loading it into the proper register. Excellent. Now we come over and execute the instruction at the target, which is, you guessed it, a load instruction. And we're following it down, and sure enough, we're loading that A value first. If we scroll over, we can see that we also hit the jump and return. This is the newer variant of the JAL instruction, and in it we're calculating where we need to jump to, which obviously we need to jump back to the instruction after the first jump and link call, which is the X1 register, which is A, at plus 0, and we get the instruction right after the original jump and link instruction. And sure enough, it's that load instruction, and we expect it to load in Bob, and it has. Excellent. And of course, right after that load instruction is our break instruction, and we go off into the black hole. So it is actually working as expected. You can see that we're starting off in our jump. We do our calculation for the target address, the return address. We now go and execute the instruction at the target address, which is a load, and then we hit the next JAL instruction. Excellent. And it is going to try to return based on, we don't care about what's in X0, but we do care about the X1 register, which has the return address. That gets loaded up, sure enough, and we found that at that location is the load word from memory, and it loaded Bob. So excellent. Everything is working as expected. Next is the load upper immediate. For that, we've returned back to the data flow diagram as expected. So we assume that the instruction register has been loaded with the load upper immediate instruction, which means that the immediate portion of the instruction is available here in our immediate module. The immediate module, one of the things it does is shift the value 12 bits to the left, which is where the instruction gets its name from. It's loading the upper bits only. So it's routed through here, and we don't want to do anything to it when we route it through the ALU, so we simply add 0 to it by setting the add operation, and then routing it immediately through to a write back into the destination register that's specified in the instruction as well. That's the load upper immediate. Now we take a look at the FSM for that instruction. So as usual, we'll start over the decode and add a new path that will take us down a new execution path. So we'll pop that open, and you can see here that we're setting our A source to 0, a B source to that immediate, which has the shifted value in it, and we're doing our write back from the immediate channel way on the MUX, and then we're setting our register right. Here we are at the HDL, and as usual, we'll start at the decode. We'll come down here, and for the LUI instruction, we'll add a new pathway into the decode state, which is right here. So U type is what we're looking for in the execution module. So we'll come down to the U type, and here it is. You can see that it's a single state, as we saw in our FSM. We've set our A source to 0 on that MUX, and our B source to the immediate field coming in on the MUX. We set the MUX for routing back into the register file to the immediate, because we want to pull it from the ALU immediate output, and we enable register writing. That's it, and then we head on over to the prefetch to begin fetching in the next instruction cycle. With the HDL in place, we're ready to look at the machine code. I've gone ahead and placed in our assembly here and ran it through the assembler, the one-line assembler that we have. It generated this statement, and we can see the upper immediate portion, the 20 bits, sitting over here in the instruction itself, and they came out of this bit code right here. And of course we follow it up with an e-break. And as usual, I've already updated the memory module with this new load upper immediate RAM configuration, and we're ready to take a look at the simulation. And here's the simulation for the load upper immediate instruction. As you can see, we passed the reset state, and we're now hitting up on the instruction. We can tell that it is a U-type load, the LUI. We can also see our register that will be loading, the destination register, and there's the machine code. We follow it down, we can see that we're doing an add on the ALU, and we're adding in the 0 value on source A, and then the immediate value that has been shifted up into the upper bits here, the most significant bits. And then that is in turn loaded into X2 or register 2. This is exactly what we expect in the U type and then the U type prefetch. And finally we add the add upper immediate to the PC. And as usual, we start at the instruction register. It's been loaded with that instruction. Now the only difference between the LUI, and this instruction is one item, and that's this pathway right here. That's the difference. Before we were adding a 0, now we're adding in the location of the actual instruction itself with the immediate value. They're both identical. They'll route back, do a write back, and into a destination register specified in the instruction itself. We're ready to take a look at the FSM for the AuiPC, and as usual we'll start with the decode statement here. So we'll open that up and scroll it over, and here we are. This is our new execute and final execution path. And here we are loading in the PC prior, and remember that the PC prior has the address of this instruction in it, whereas the PC is always pointing forward one instruction because the decode statement over here has bumped it up. So we know that we're going to take the current PC and add in the immediate that's in the instruction, very similar or identical to the LUI, except that we were using a 0. Now we're using a prior, and we're going to do a write back into a destination register. Here we are at the HDL. And as usual, we'll start at the decode statement. We'll add in our AuiPC type, and there it is. This will route us down into the execution section. So let's go down there, and here it is. And the only difference between the U type and this type is the A source. Otherwise, they're identical. Here is the machine code for the AuiPC instruction. And as usual, I've taken this assembly here and copied it into our one-line assembly, and it generated our instruction. Now you can see in it the DEAD, the dead portion of it, and you'll see when the instruction runs, it's going to actually add this and this together. That's the PC prior right here. This would be PC, which is always ahead by 1 because of the decode statement. So I've updated memory module and filled out the RAM for it, and we're ready to run the simulation. And here is the simulation for the AuiPC instruction, and as usual we've gone past the reset. We've identified it as a U-type A instruction. There's our machine code right there, and here is the PC prior that we will be adding to the dead that we loaded in, and we get dead plus 4. That's loaded in to registry 3 right here. So the instruction is doing exactly what we expected to be doing, and of course we fall into the black hole on the next load right here. Well, that finishes the RISC-V RV32i ISA with the caveat of only a minimal implementation of the two system instructions eBreak and eCall. But there's still more to do, and as such, in the next episode we'll look at building even more complex programs, at least as far as what we can put into the simulator in GTK Wave. Too many instructions and the thing becomes very difficult to see. So until next time, peace.